Last video, we solved two sum by swapping a nested loop for something called a hash map, and the complexity dropped from big of n squared to big of n. I told you that lookup was basically instant, big of 1. I didn't tell you why. Today, we open it up. Say you want to store a value and find it again later by some key, a username, a word, anything. The dumbest possible approach, stick it in an array and to find it again, scan the whole array. That's big of N, the exact linear search from last video. A hash table's entire purpose is to skip that, scan completely. Here's the trick. Instead of searching for where something is, calculate where it must be. A hash function takes a key, a string, a number, anything, and turns it into a number. That number becomes a direct index into an array. No searching, you compute the address and go straight there. What's the word? Cat goes through the hash function, comes out as say 14, we store it at index 14, look it up again, same word, same hash, same index every time. That's the entire idea. One calculation, one jump, done. Big of 1. In code, this is generally just two steps. Index equals to hash key, modulo array length, then array index equals to value. Compute the hash, take it modulo the array size, so it fits, store it. Looking something up later runs the exact same two lines, no loop. That's why it's big of 1. The operation count doesn't depend on how much is already stored. But here's the problem. Nobody mentions until it bites them. Hash functions aren't magic. Different keys can produce the same index. Cat and dog might both hash to 14. Now what? You can't store two things in one slot. This is called a collision, and how a hash table handles it is the entire difference between a fast one and a slow one. The most common fix, chaining. Instead of one slot holding one value, each slot holds a small list. Cat and dog both land at 14. Fine. 14 now points to a tiny chain. Cat, then dog. Looking up dog means landing at 14 instantly, then walking a short chain to find it. Code-wise, instead of array index equals to value, it's array index dot append value, and that lookup works the mini list at that one index, usually just one or more two items, not the whole table. So what's the real complexity? If collisions are rare and chains stay short, it's still effectively big of 1. One hash calculation, one jump, a tiny walk of 1 2 items. But if everything collided into one slot, you would be walking a chain of n items and you are back to big of n, the exact thing we were trying to avoid. This is why a hash table's real world speed depends entirely on how good the hash function is and how full the table gets. That fullness has a name, load factor. How many items you have stored divided by how many slots exist. To get full and a collision stack up, chains get longer and your beautiful big of 1 quietly degrades toward big of n. The fix: when load factor crosses a threshold, the table resizes, usually doubles, and every single existing item gets rehashed into the new bigger array. That resize operation is expensive, big of n, but it happens rarely enough that averaged over many inserts it barely costs anything. There is a name for that kind of cost: amortized big of 1. Same nuance from last video applies here. Average case with a reasonable hash function and load factor big of 1. Worst case, if every key collided into the same slot, you would be searching a single chain of n items big of n. A hash tables is only as fast as its hash function is good at spreading keys out evenly. And the cost for all this speed, big of n space. You are holding every item plus some empty slots reserved ahead of time so collisions stay manageable. That trade-off, spend extra memory by near instant lookup, is the whole bargain a hash tables make. Let's close the loop from the last video to some optimized version. One loop at each number, you check is target minus this number already in my hash map, then add the number in. Now you know exactly what the line is doing underneath. Has the number jump to its slot, check or insert. One has one jump. That's why it's big of 1 per check and big of n for the whole loop. Not a trick, just a hash table doing exactly what we just took apart. So a hash table isn't searching, it's calculating where something already is. Collisions are normal, not a bug, and chaining handles them. Load factor and resizing keep it fast over time. Average case big of 1, worst case big of n, and it spends big of n space to get there. Next time you reach for a dictionary, a map, a set in any language, that is what's exactly running underneath.